partially decryptable commitments from lattice and application by Mohammed Esrin, Ron Steinfeld, Raymond Zhao, and Mohammed will give the talk. Please start.
Yep, thank you for the introduction. So our work is about a new tool that we call Verifiable partially decryptable commitments. Its instantiation in the lattice setting and applications in the context of private blockchain payments. I'm sure many of you know what a private preserving protocol is. We have a bunch of parties that are exchanging some messages. They might be doing some local computations. And due to kind of privacy concerns, we want to hide the user identities, so they're kind of like encapsulated. And we also want to hide the messages that are exchanged, so they're also maybe like encrypted or encapsulated in some other fashion. And there are cryptographic tools we can use in such protocols like commitment schemes, zero-knowledge proofs, and encryption schemes. But a practical issue with privacy-preserving protocols is that the adversary may actually exploit this privacy or anonymity features of the protocol to gain, for example, to get away with his illegal activities. For example, he might have injected some ransomware into the Alice's computer, and he might be asking for a ransom of $1 million to be paid in Monero so that he can hide his illegal transaction records. Okay, so from a practical perspective, to resolve such issues, what we might do is we can have the same thing as we had before. So the outside parties still does not see the private information, but we can introduce an authority into the system who has a secret trapdoor that is only known by the authority. And using that secret trapdoor, the authority may be able to de-anonymize users in case of misbehavior or illegal activity. And in this setting, we would have a what we call an auditable privacy preserving protocol. And then the adversary can say, oh, okay, that's actually Bob who is misbehaving. And similarly, the authority can also kind of decipher the exchanged messages if needed. And there are many examples where this accountability or auditability feature is needed. And our work focuses on the blockchain protocol applications. And it actually turns out that, like in many existing protocols, they are built on commitment schemes to hide the secret information. And in general, there is no decryption feature in commitment schemes, especially due to the compression. And there's no way to recover partial secret information, even if it's desired. So if you want to get this auditability feature that I mentioned, we can just switch to encryption. But then there are some drawbacks. And in particular, in many protocols, we need to commit to this kind of like a very high entropy auxiliary messages that need not be recovered in decryption. And if we switch to an encryption instead of a commitment scheme, then it's going to come at a significant communication cost because we cannot do compression in the encryption setting. And the goal of our work is to kind of get around this problem and introduce a partial decryption for commitment schemes in a verifiable manner. Okay. Let me kind of list our contributions in this work. So we first formalized this notion of verifiable partially decryptable commitments, and VPDC for short. And this is an extension of a commitment scheme with a matching misproof and non-interactive zero-knowledge proof to provide partial decryption. And in this setting, partial decryption is really critical because we don't want to recover the full message. We just want to recover a part of the message, which is going to be probably has a much lower entropy than the whole message that is being committed, so that we can get a compression for the non-decryptable message part. And this is the main difference from these notions of verifiable encryption and proofs of plain text knowledge, which are kind of like similar notions. And then we have these generalized results that apply to these relaxed misproofs. So I'm not going to talk about what these things are, but we basically have a kind of like a lifting theorem that says that if you can do decryption in a non-relaxed case, then you can also lift this to relaxed decryption for a wide class of protocols. And then we have a novel decryption method for this commonly used hash message commitment scheme in the lattice setting. And here we make use of these gadget vectors to enable a regex style decryption. And then finally, we have an application to a private blockchain payment system from lattices, and we extend it to make it auditable. And the main goal here is that we want to make as minimal changes as possible. Actually, this is one of the goals again for our VPDC notion. We just want to take existing protocols without replacing the existing NISCs and we just want to change the commitment scheme or extend it to VPDC to make the whole protocol auditable. Okay. And yeah, I would just listed here some communication results, so you don't really need to understand everything here. But the important point here is that we just have additional 3 kilobytes in the proof size. So it's just a 3% increase to get auditability. And so it's very minimal. And in terms of computation, again, there's just very minimal increases for like in all aspects like key gen, transaction generation, and verification. And this auditability feature that we have in this matrix AU has interesting features. So we can have multiple auditors auditing the same transaction without revealing their individual trapdoors. And each user can choose their own auditors, and even they can choose not to be audited at all. And we can also have the system enforcing auditability, and so that they cannot avoid auditing. Yep, that's all I wanted to say. Our work, the full version is on ePrint. The source codes are available. And if you have any questions now or later on, you can email me or ask now. Thank you.
Thanks for your talk. And are there any questions or comments? Okay, so I have one question. Can you see page 9? Is this a definition of auditability or its feature?
No, this is the kind of like the features of auditability that we get.
Okay.
Like having multiple auditors, and then like users choosing their own auditors and maybe choosing not to be audited, and then the system being able to enforce auditability so users cannot avoid being audited.
Okay, thank you. So anyone have questions or comments? So can you see the experimental results? I guess
yep.
you showed.
Yep. Is it this one, computation or communication?
This is a comparison or just your?
Yeah, this is comparison with the original protocol, the one that doesn't have auditability. And so this is matrix, the original one. And we extend it to be auditable. We call it matrix AU. So the auditable version has very little overhead over the original protocol.
Okay, so so your auditable protocol works with almost the same efficiency.
Yeah, that's right. So because we are just kind of changing one of the commitments to a VPDC, and it comes at a very minimal cost. And that's kind of like the goal that we want to change.
Okay, thank you.
Yeah.
Anyone, there are any questions or comments? Okay, so my last question, can you construct this protocol from not lattice assumption by other assumptions?
Yeah, we mainly focused on the lattice-based one, and I think it's interesting to see if something like this can be done outside the lattice setting. But we haven't looked at it yet.
Okay, thanks. Are there any questions or comments? Okay, so it's about time. Thanks, Mohammed.
Thank you.
So let's go to the next talk. Okay, thanks.
Okay, can you see my screen?
Okay, yeah. So the next talk is making private function evaluation safer, faster, and simpler by Liu and C1. C mean you. Okay, so we give the talk. Please start.
Okay, thank you very much. And hello everyone, I'm Liu. Today I will present our work, making private function evaluation safer, faster, and simpler. This is the Joel and C1 and Xiuming Liu. And PFE, namely private function evaluation, considers such a two-party case. There is the party Alice and a party Bob. Alice has input a private function F and private input S, and Bob has private input Y. They intend to compute FSY, and then one or two parties receive the input. And here Bob receives such an input, such an evaluation result. And this is different from standard secure function evaluation because the function F here is private and is the input of one party. And to realize PFE, there are some approach. It's very straightforward to use fully homomorphic equation to realize PFE. However, today, fully homomorphic equation still has very high computational overhead. And the second one is to use universal circuit. Universal circuit is a circuit that tells us input the description of a circuit, another circuit C and S, and compute CS. However, for universal circuit, for the circuit C with size n, the corresponding universal circuit has size theta n log n, and there is an additional log n overhead. And at the same time, the constant factor and low order terms are also significant. And the third approach is to avoid the usage of fully homomorphic equation and universal circuit. So there is an approach based on Oblivious evaluation of switching network. However, it still has log n, additional log n overhead. And starting from Katz and Malkat in 2011, they proposed a protocol with linear complexity with respect to the size of the circuit and its constant route. And recently, it was shown that the passively secure such a protocol outperforms the state-of-the-art passively secure universal circuit-based PFE protocol. And there are also some improvements of the passively secure PFE protocol. In the paper MS13, they generalize and impose the original passively secure PFE protocol. And then reusability property is added with respect to given party or the original protocol to obtain better performance. And this reusability means that we can have one initiation for the private function F and then multiple evaluation of F on different input. For example, like this, Alice can perform an initiation for her private function F with Bob. And then they can use different input value and compute different evaluation results. So only one initiation is needed. And what about active security? In the original paper, the author introduced how to achieve active security against malicious input provider. So the input, the provider Bob here can be malicious. However, they need to assume that the function provider Alice is semi-honest. And then will provide a protocol that is full security. However, in this protocol, the numbers of routes is equal to the numbers of gates. So to the best of our knowledge, there is no constant route actively secure PFE protocol with linear complexity. And in our work, we provide the first actively secure constant route PFE code protocol with linear complexity. And we also improve the reusability, and we call it global reusability. And we also provide a PVC security version of the protocol. And here, global reusability means that, for example, like Alice here, it can provide a global initiation for her private function F. And then a party Bob can use this private function, use this global initiation information, and then directly start the evaluation of private function F when Alice using the different inputs. And at the same time, a party Charlie can also use this global initiation information and then start the evaluation of private function F directly when Alice. So our approach is here. We divide the protocol into two phases, the initiation phase and the evaluation phase. And then for the initiation phase, we design zero-knowledge protocol for discrete logarithm and extended permutation. And here, extended permutation is used to describe the topology of the circuit. And we obtain a AT security, we achieve AT security against Alice, so the function provider. And then we can use Fiat-Shamir heuristic because the message from Bob is random. And we can make the initiation phase non-interactive and then obtain fully AT security. And for the evaluation of private function, we can use classical approach for Gabor circuit to obtain fully AT security. So combine these two phases, we obtain AT secure constant route PFE protocol with linear complexity. So that's all of my talk. And if you are interested in our work, you can see the full version on ePrint. Thank you very much.
Thank you for your talk. So are there any questions or comments? Okay, so I give one question. Can you show your table which compare your work and your previous works?
Oh, okay. Like this?
Yes. Is this work provides the first publicly verifiable covert security? It's okay.
Sorry.
PVC. The security, PVC security. This work first achieves this security.
Yeah, it's faster than the AT security version.
And so your work achieves the first security and it's very efficient and reusable. It's okay.
I think our work, the main contribution of our work is provide the first AT secure constant route PFE protocol with linear complexity. And there are some additional bonus, for example, like global reusability. And we also for practical use, we also provide the PVC security version because the two phase, like the initiation phase and the evaluation phase, is very suitable to transform the AT security version to PVC security version, and you can obtain better efficiency.
Okay, thank you. So are there any questions? Okay, so I give one more questions. Also, it may be not very efficient. Can we achieve the same security and the reusability by using FAC?
Maybe we. I don't know. I don't try
okay.
FAC. Maybe it can be a future work to try to see can. But I don't know. I don't know this.
Okay. Are there any questions?
Yeah, I have a short question. So, like, I'm not sure about like reusability. So, yeah. So maybe you can use like you can reuse like some initiation like information. I don't know how much like you can reuse some information, right? So
yes,
and you can omit some procedure, initiation procedure, right? So
yeah,
and is it like initiation procedure like heavy in general? So in like among these schemes,
the initiation is for the function. So
yeah,
it's only for the function.
Yeah. So yeah, I want to know like how important this like functionality and feature.
Because for previous work they mix the initiation and the evaluation together for most of the previous work, and so we divide them into two phases, and now the initiation only need to execute one time, so it can gain better efficiency.
Okay, yeah. So like I mean, you can improve some efficiency. I mean, you can omit like this phase, right? So you can only like run this initiation only once, right?
Yes.
So yeah, okay, is it okay? Thanks.
Thank you.
Okay, so thanks, E, and we go to the next talk. Thanks for a nice talk. Okay, so next speaker, can you share your slide? Oh, thanks. So the next talk is two-round Oblivious linear evaluation from running with errors by Pedro Blanco, Nico Dotrin, and Paolo Matteo. Okay, so please start your talk.
Pedro, if you're speaking, we are not getting any audio from you.
Hello?
Yes, I can hear you.
That's better.
Sorry. Okay. Okay. Hi, everyone. This talk is about two-round Oblivious linear evaluation from LWE, and this is joint work with Nico Dotling and Paul Mateus. So first, what's Oblivious linear evaluation, or OLE for short? OLE is a protocol between a sender on the left side with input A and B coming from a finite ring, and the receiver on the right side with input X. In the end, the receiver should get a linear combination A plus XB. In terms of security, we want that the receiver learns nothing about the sender's input, A and B, apart from what is trivially leaked by the output, and that the sender learns nothing about the receiver's input X. OLE is usually seen as the arithmetic generalization of the well-known Oblivious transfer primitive. In terms of applications, OLE has found numerous of them, especially as a building block for two-party secure computation schemes in a variety of different settings. So in this work, we ask whether we can build efficient and maliciously secure two-round OLE protocol from presumably post-quantum hardness assumptions. And we show that we can build an OLE scheme which is secure against malicious receivers, where security holds statistically, and against semi-honest senders, given that the learning with errors assumption is hard. And the protocol runs in 2 rounds. So how do we obtain our result? We first generalize the famous OT scheme by Picard, by Kuntanathan and Waters, or PVW, into an OLE scheme. And this step goes relatively easy if we look at PVW from the right perspective. Then, regarding the security proof, correctness, and semi-honest security against the sender follows very easily. But if we were to adapt the proof of PVW for a malicious receiver, then we would run into problems. To see this, recall that at some point in the proof of PVW, the simulator needs to decide if a vector Z over ZQ is close to the row span of a matrix A. And the way they solve this problem in PVW is by allowing the simulator to run over all possible values of alpha in ZQ and check if there is an alpha such that alpha times Z is close to the row span of A, which can be checked given a lattice trapdoor for the matrix A. Since the simulator needs to run over all possible values of Q, they require that the modulus Q is polynomial in the security parameter. This is okay for OT, but it's not ideal for OLE, as we would like to have OLEs over any finite ring, including rings with super polynomial size. And with this approach, we would be stuck with the polynomial size rings. So the main technical challenge that we solve in this work is to devise a new extraction mechanism that decides if there is an alpha such that alpha times Z is close to the row span of a matrix A for any modulus Q, even for a super polynomial modulus. As additional results, we show how to extend our protocol into a batch variant where the receiver can commit to a bunch of inputs and that achieves better communication complexity. And we also show how to extend the protocol to allow for malicious senders using more or less standard current choose techniques. That's all. Thanks.
Thanks. So are there any questions or comments? Okay, so can you explain why we have to study the super polynomial modulus, since I guess polynomial modulus should be more efficient, I guess.
Yes. But in some applications, you might require an OLE over larger fields. Okay.
Okay.
So yeah, that's the reason. So, for example, you might want an OLE over a field of exponential size.
Yes. Okay. Any other questions or comments? Okay, so I'll give another question.
Sure.
You said you focus on the post-quantum security, but can you obtain the similar results by a Diffie-Hellman type assumption?
Actually, no. We use very specific lattice-based techniques, which we don't know how to do in the group setting.
Okay, so can you explain which part did you use the lattice-based technique?
Yes. So in the proof of malicious receivers, we need all of these lattice gadgets like lattice trapdoors, and yes, we need lattice trapdoors, for example, and that's one thing we don't know how to do using in the group setting.
Okay, thanks. Any other questions or comments? Okay, so can you show the page of overview of your work? I guess
sorry?
how you constructed the protocol. I guess it should be page 5 or 6.
Okay.
Okay. So as you said, proof against the malicious security of the receiver is the most technical hard part.
Yes. Yes.
And here you use the lattice space technique.
Yes.
So actually, okay.
Yes, this is where we used all of these lattice space techniques. Yes.
Okay, so any other questions or comments? Okay, so let's go to the next talk. Thank you for Pedro. Nice talk. Okay, thank you. I can see your slide. So the next talk is improved constructions of anonymous credentials from structure preserving signatures on equivalence classes by, I think, Connolly, Pascal Lafocade, and Octavio Perez Kempner. Okay, so Octavio will give the talk. Please start.
Thanks for the introduction. It's a pleasure to be here. So let's get started. Attribute-based credentials, or ABC for short, allow a user to get a certified set of attributes from an issuer. This way, users can authenticate themselves by showing some of the attributes to a verifier. Anonymous ABCs allow users authentication without leaking any other information besides the shown attributes. Some systems can be multi-shown, which means that they allow an arbitrary number of unlinkable showings. Finally, we can also have multi-authorities ABCs, which allow users to obtain a single credential for attributes potentially coming from different authorities. In this work, we consider multi-show ABCs in the single authority setting. The main differences between the recent constructions include the expressiveness, the efficiency in terms of computational cost and bandwidth, the communication in terms of whether or not they provide non-interactive features, the security model, and if they handle and how revocation features. One thing that none of the previous work addressed was the problem of leaking the issuer identity. To address this issue, we propose a notion called signer hiding, and it refers to the ability to hide the identity of the issuer during showings. This concept was also recently developed on concurrent and independent work under a similar name of issuer hiding and presented at CANS 2021. So if we consider the following scenario, where we have a seller offering discounts for European non-Spanish residents, a user could claim that it's French, but that would give away too much information to the verifier. And furthermore, if the credentials are issued by home countries, no matter which attributes user decide to disclose with the verifier, the home country will be leaked. What we want in scenarios like this one is to avoid such things and find a way in which users can convince the verifier without giving away information from their country of origin. A way to convince the verifier about being European but not Spanish is to hide the issuer's identity in a set of valid countries, like in this example. So I will now comment on how we went towards more improved constructions of anonymous credentials. So in this regard, our work followed the line of work from Fuchsweier, Hanser, and Slamanik from 2019, which is based on structure preserving signatures on equivalent classes, or SPS on EQ for short. And in this regard, we focus on improving the following aspect: the expressiveness, extending the accumulator using the credential scheme, the efficiency, leveraging user and verifier costs, the security model, and we also added support for signer hiding showings, which was the missing feature I commented before. In order to present our results, it would be useful to use this diagram. And if we look at like top down, you can see that the boxes in grays highlight our contributions. The first one was related to an improvement on the structure preserving signature that we use from a recent construction that was proven secure using standard assumptions. Here we replaced an OR proof that was being used with one that is more efficient, and also added an extension to support what is called mercurial signatures, so that the signature can act on both equivalent classes on the message space, but also on the key space. Then we improved the set commitment scheme that was being used before by applying an extension to support batch non-membership proofs, and also a proof of exponentiation that is outsourcing some of the computational cost from the verifier to the user. We instantiate these primitives on the previous ABC framework, but then we added the signer hiding functionality, and of course we had to support the security model. We updated it so to take into account these modifications. So going to the signer hiding details, the main idea is that one first randomize the credential and the issuer public key consistently. Then one presents to the verifier along with a proof of correct randomization of the issuer's public key. And this is to avoid, for instance, that the user self-signs his own credential, randomize the public key, and presents a public key that is not coming from a valid authority. And to do this, we use a 1 out of n OR proof, which is a fully adaptive NISIC argument. And the advantage of this is that users can select arbitrarily long sets of public keys to compute the proof with linear cost. Like in the example, the user can say it's coming from a European country, but without telling which one to the seller. So to conclude, well, our results explore multiple paths to extend the ABC framework from FHS 19. We obtain a more flexible framework leveraging different trade-offs. The proposed signer hiding notion enables more use cases. And as future work, we consider that exploring the use of aggregatable signatures with SPS on EQ in the multi-authority setting could enable even more use cases. And also that devising other ways to define equivalent classes could lead to new and more efficient constructions. And the reason behind it is that currently unknown constructions rely on Diffie-Hellman-like assumptions. That would be all. Thank you very much for your time. I'm happy to answer any question you may have.
Okay, thanks. So are there any questions or comments?
Hi, I was wondering, the original equivalence class signatures had a weakness in that if you know 2 or more of the scalar elements of the message, that lets you recognize the message even after randomization. This was big enough that mercurial signatures had to weaken their anonymity model. Have you considered whether that affects your construction, particularly with regard to signer hiding?
Okay, so let's go by part. The construction used on the mercurial signature paper is coming from the original FHS 19 paper. In our work, we did not use this construction as a baseline. We could instantiate our results with the mercurial signature construction coming from the mercurial signature paper that you're referring to, which is based on the original, on the first SPS on AQ. But we took a different path. So let me go back to the slide here. So as I said, the structure preserving signature that we are using as a baseline is one coming from Khalil, Slamanik, and Dakiliarian. Okay, and this it's a different type of construction. So the issue that you're mentioning, I don't think is present on this construction, but we can discuss it more in detail offline. Now, thinking about the original perhaps, construction, the length of the vector, because the length of the message vector used in our anonymous credential system, it's of length 5. I don't believe that there is a vulnerability issue here, because for the Diffie-Hellman tuples you have the DDH, and should be fine. But maybe you can specify a bit more your point. If sorry if I missed something.
Yeah, that's fine. We can go into more detail on Zulip.
Okay, yeah, happy to do so. Thanks.
Thank you.
So any other questions or comments? Okay, so I give one question. I'm sorry, but I cannot follow the presentation very much. And what is the main benefit of your work?
Okay, so you could say that we added the feature of managing the signer hiding part, which was a missing feature on the previous work. All of the different lines of work always rely on a signature construction. Okay, and the thing is that once that your credential is represented as a signature, the public key that you use to verify it leaks the identity of the issuer, and in some contexts, the identity of the issuer may be enough to reveal the identity of the user. Suppose that you're using a credential system on a federated level where you have a different set of authorities. If I know that the credential is coming from a particular authority, that may be enough to de-anonymize the user. Okay, so I want to hide the user identity as much as I can. This is what we achieve with the signer hiding notion, for instance. Then there are other improvements in terms of efficiency related to outsourcing some of the computational cost in the showing protocol from the verifier to the prover, and also in terms of the expressiveness by extending the features of the underlying accumulator that is being used to represent the credential. And this is where the proof of non-membership comes into play. Before that, you only have selective disclosure of attributes. Let's say I can say things about the attributes that I have, but it's difficult for me to tell you things about the attributes that I do not have. Now, with this extension, it's possible for you to prove that you do not have a certain set of attributes, and this also with a single proof for the whole set of attributes that you want to say I don't have them, for instance.
Okay, thanks. So let's go to the next talk. Thanks, Octavio.
Thank you.
All right, cool. Let me share my screen really quick. Cool. Is it working?
Please wait.
Okay.
I cannot see yet. I cannot see your slide.
Okay, that's weird. It says it's sharing.
Are you using two monitors by chance?
Sorry, somehow Zoom crashed. Let's try again. Yeah, now can you see it?
Okay, it's okay. So the next talk is Traceable PRS for collision resistance and active security by Sarasi Maitra and David Wu. Okay, so please start your talk.
Great, thanks for the introduction. So this talk will be about traceable pseudorandom functions in this joint work with Sarasi Maitra. So the main goal of traceable cryptography is roughly as follows. Some content distributor has some program key, and it wants to give out copies of this program key to a set of users. Now, each of these copies are going to be marked with an identifier, which might be the username or some serial number. And the objective is that each user, once they have their own copy of the program, they should not be able to produce a new copy of the program that does not contain the identifier associated with them. And this is a useful primitive for protecting against the unauthorized distribution of software. Now, the focus in this work is we're going to focus on one particular class of problems, namely protecting pseudorandom functions, which in turn give us ways of protecting various symmetric cryptographic capabilities. So in this particular setting, the program of interest is a pseudorandom function. It has a key for the PRF baked inside it, takes an input, and evaluates the pseudorandom function and produces the output. Our goal is to be able to embed some kind of mark or identifier within the program such that the mark is basically embedded within it and cannot be removed without destroying the functionality of the program. This notion is a very conceptually similar to watermarking, but provides a much stronger security guarantee. In particular, the security guarantee that we're interested in is we're saying that if a program C that the adversary produces manages to break pseudorandomness, then that program can be traced and we can identify which program was used to build this new decoder or new distinguisher. So the goal is to basically construct a program that has the tag embedded within it, such that that tag can later on be recovered, given only black box access to the program itself. This primitive suffices for realizing many kinds of traceable primitives, such as traitor tracing, and this really follows from the fact that encryption can be built from pseudorandom functions. Once you can trace a pseudorandom function, you can trace any class of primitives that can be built from the pseudorandom function itself. So if we look at existing constructions of traceable pseudorandom functions, what do we know? Well, from standard lattice assumptions, we know how to build what is called a single key traceable pseudorandom function. And what this means is that security holds assuming the adversary sees a single marked program. It turns out that this construction is actually completely broken if the adversary just sees two marked programs. In this sense, we say the construction is not collusion resistant. Namely, given two marked programs, you can completely remove the mark from the program entirely. If we ask about fully collusion resistance, namely where security holds even against adversaries that can see arbitrarily polynomial number of marked programs, we say it is fully collusion resistant. Turns out constructing traceable pseudorandom functions with full collusion resistance is non-trivial, and we only know how to do it from indistinguishability obfuscation. So a natural question, and the one that we ask in this work, is whether we can hope to build collusion-resistant traceable pseudorandom functions directly from LWE. And in this work, we provide a new generic approach to upgrade any single key construction into a fully collusion-resistant construction through the use of something called fingerprinting codes. Now, fingerprinting codes are an information theoretic primitive, and so combined with the existing constructions of single key traceable pseudorandom functions, we obtain fully collusion-resistant traceable pseudorandom functions from the same underlying assumption. Now, there is one caveat in our construction in that it only supports embedding tags who's from a polynomial size set. And it's an open question to try and extend it to also get tags that are much larger. Let me now give you a brief overview of how the construction operates. So in a fingerprinting code, we basically associate a code word with each identifier. So the identifiers here are the numbers 1, 2, and 3, and the arrays correspond to the code words. Now, the model that we work in is the following. Imagine an adversary comes along, and it gets some subset of these code words, here code words corresponding to 1 and 3. And the adversary's goal is to craft a new code word, but with the stipulation that in certain positions, it can only choose the value as long as it matches one of the code words that it is given. And the goal of the adversary is to construct a new code word that happens to decode to one of the ones that it was not given. Security for fingerprinting codes says that no adversary would be able to do this, provided that the adversary has to respect this constraint. Now, once we have a fingerprinting code, it's actually fairly straightforward to use it to boost a single key construction into a collusion-resistant construction. The idea is as follows. The traceable PRF is going to be defined to be L copies of the single key traceable PRF, where L is the length of the fingerprinting code. So we just simply combine them by just XORing all of these independent copies together. Now, to embed an identity or to mark a particular pseudorandom function, what we do is we start by taking the identity, we encode it using the fingerprinting code. This gives us a code word. And then we basically embed the ith bit of the code word and the ith key of the single key traceable pseudorandom function. So we're going to mark it L times 1 for each bit of the code word. The idea is now as follows. Observe that if the code words all agree on a particular position, then all of the marked keys that the adversary sees also are marked with the same bit in that particular position. The adversary only sees a single marked key, and thus we can actually appeal to single key security, the underlying security of the traceable PRF, to enforce the constraints of the fingerprinting code model. Now suddenly, the security of the resulting traceable PRF reduces to that of the underlying fingerprinting code. So just to briefly summarize, In our work, we propose a generic approach that upgrades any single key construction into a fully collusion-resistant construction through the use of fingerprinting codes. And so under LWE, we now can have a fully collusion-resistant traceable PRF with exactly the same properties as we had previously. It turns out that similar extensions to our technique can also be used to achieve stronger security. In this talk, I won't go into details, but basically we can define an active notion of security for the setting of traceable pseudorandom functions and show that our new boosting technique also allows us to satisfy this active security notion. And I'll leave you with one open question, which is, can we try and build collusion-resistant traceable pseudorandom functions with a super polynomial size identity space from standard assumptions? So we know how to do this for trader tracing, but we don't know how to do it for traceable PRFs. And with that, I'll wrap up. Thanks for your attention.
Okay, thanks for your talk. So are there any questions or comments? Okay, so I'll give a question. Although you may have been said, I don't know what is the technical limit to achieve super polynomial identity space. Why you cannot achieve the...
Yeah, that's a great question. So the limitation actually comes from the fingerprinting codes. So if we just look at traceable pseudorandom functions in a single key setting, there we know how to get super polynomial identity space. But for a fingerprinting code, basically the length of the codes that we have today grows with the size of the identity space. So if you have a super polynomial identity space, the size of the fingerprinting code that you would need would also be super polynomial number of bits. And as a result, the construction would no longer be efficient.
Okay, so we have a question on chat. Can you talk about applications of traceable PRS and what state is required to be maintained over time for the tracer?
Yeah, so traceable PRS is basically, I would say that the primary application is a different way of getting trader tracing. So essentially, whenever you want to protect a pseudorandom function, be it for the pseudorandom function, the PRF key, let's say for a decryption system, or maybe a PRF key in a challenge response authentication system, if you want to protect the key, a traceable PRF provides a way to do that. In terms of the state that needs to be maintained over time, basically in a secret tracing setting, the only state that you need to keep track of is the secret tracing key. So essentially, given any program that can basically preserve the PRF functionality, there's a tracing algorithm that will be able to extract the identity from that program. So you don't need to make any assumptions about which programs have been given out or which identities have you given out programs for. All you need to keep track of is the secret tracing key. Now, in the public tracing setting, you can actually do even better. Here, there's actually no need to keep track of any state. Just given any program and the public key for the scheme, you would be able to identify who was the one that created that program. But the main applications are the protecting against distribution of software, especially software built from pseudorandom functions or other cryptographic capabilities.
Okay, thanks for your nice talk. Yes, cool. And this is the last talk of the session, Cryptographic Protocols. Let's thank all speakers of this session. Okay, so we move to the next session tools. And the next speaker, can you share your slide?
Okay, can you see my slide?
Yes, but you use full screen. Okay, so the next talk is Radical Isogenies on Montgomery curves by Hiroshi Onuki and Tomoki Moriya. Okay, please start.
Thank you for the introduction. I talk about radical isogenies on Montgomery curves. This is a joint work with Tomoki Moriya. Radical isogenies are one of the techniques speeding up isogeny computation, which are formulas for computing a repeating isogeny of the same degree, and were proposed by Kastrik, Decroux, and Berkotren at EjaCrypt 2020. Radical isogenies use radicals I mean radical isogenies use an nth root for an isogeny of degree n. CDV shows that radical isogenies accelerate small degree isogeny computation in CSAF. CSAF is an isogeny-based key exchange protocol. The original radical isogeny formulas are constructed on Tate-normal forms, which are forms of elliptic curves. The original radical isogenies in CSAF need to transform a Tate-normal form into a Montgomery curve because computation except for radical isogenies is more efficient on Montgomery curves. Furthermore, we need to choose the nth root corresponding to an isogeny of degree n in CSAF. If n is odd, it is easy to determine. But in the case n equals 4, CDV conjectures the choice of the fourth root, but it was not proven. In this work, we constructed radical isogenies of degrees 3 and 4 on Montgomery curves. In addition, we proved the conjecture on n equals 4 in CSAF. These figures show a comparison of our formulas and those of CDB. In CDB, we need to transform curves at the beginning and the end of radical isogenies. Here, these isogenies have the same degree. And the transformations are needed for isogenies of other degrees. On the other hand, in our work, we don't need any transformations, but we need some small computation at the beginning and the end of radical isogenies. This shows the cost of radical isogenies and the computation at the beginning and the end. Here, E stands for exponentiation, M multiplication, A addition, and I inversion in a finite field. Heavy operations are E and I. As you can see, the costs at the beginning and the end in our formulas are much smaller than those of CDB. However, this improvement is small in the total cost in CSAF. As a result, our formulas slightly improve the efficiency of CSAF. Our second contribution is determining the choice of the fourth root in CSAF. For Montgomery curve defined by this equation, we define its modified Montgomery quotient small a as this. Here, the sign is determined by the Legendre symbol of a value depending on large A. Then, our radical isogeny of degree 4 is computed by this. Here, A prime is the modified Montgomery quotient of the codomain of a radical isogeny of degree 4, and alpha is the fourth root of small a computed by this exponentiation. And from this theorem, we can obtain the conjecture on n equals 4 in CSAF. That's all. Thank you for listening.
Okay, thanks for a nice talk. So are there any questions or comments? So I have one question. What is the application of your work? I mean, the CSAF is the only application, or your work is more generic one?
Now, currently, known application is only CSAF or CSAT, so C-side-like protocol. But I think that for example, a random walk in isogeny graph is potentially application candidate.
Okay, thanks. So any other questions or comments? Okay, so let's go to the next talk. Thanks, Hiroshi.
Thank you.
The next speaker, can you share the slide? Okay.
Okay, can wait a minute. Okay. Okay.
Okay,
is that work?
Okay, I can see your slide. The next talk is was a simple lattice gadget toolkit by Shirio Zhang and Yan Yu. Okay, please give the talk.
Okay, thanks for the introduction. This is work about towards a simpler lattice gauge toolkit. This is a joint work with Yang Yu. Lattice-based cryptography offers powerful advanced cryptographic primitives, FHE, ABE, and more. Many advanced lattice systems use the lattice gauge that is defined by the special vector G. And given C, the associated algorithms ask to find some well-distributed X such that the inner product of the X and the gauge vector is equal to C modulo Q. And typically, we want the output X is drawn from some discrete Gaussian or its relation is a sub-Gaussian. Despite gauge Gaussian and sub-Gaussian sampling are simple and efficient for power B modulus, but the algorithm become complicated and slow for upstream modulus. Despite that, studying the efficient gauge algorithms is both theoretical and practical interest. On the one hand, for better performance, many lattice systems use the ring structure. For further speed up in the ring sighting, they often use the NTG. The user called prime modulus supporting NTGs. And on the other, in many advanced crypto systems, the size of Q is quite large. So to compact with the architecture, we already used some CRT modulus. And in this case, the Q cannot to be the power B. Towards a better practicality of the gauge toolkit, we present to randomize the gauge algorithms for upstream modulus. We present a new gauge Gaussian simpler that avoid floating point arithmetic in existing algorithms. And compared with the previous algorithms, our simpler is achieve the same quality and symptotically complexity, but is simpler and highly parallelizable. And we also propose a new sub-Gaussian simpler. It's simple, fast, and need asymptotically less randomness. And our simpler is convenient to get close or even better quality in practical. First, we will show our new gauge Gaussian simpler. The framework of our algorithm is the packet Gaussian simpler, and we use the same metric factorization shown in Genius and essential n-chain. So our algorithms follow the same rhythm, but we implementing the step one, the perturbation sampling differently. Actually, the floating point arithmetic is from the perturbation sampling in previous work. They use the Kolaski decomposition to find the square root of a gradient metric. So to avoid of the floating point arithmetic, we employed this integral metric decomposition with A and G, and G is diagonal. With such an integral metric decomposition, the perturbation sampling can be done by applying transformation of A on the discrete Gaussian, which is simple and highly parallelizable. And our idea is inspired by the work of Dukas, Galbraith, Brett, and Yu. But there is a technical difference is that the middle metric G is diagonal, but not identity metric. So this reduce the size of A. It's only K plus 2 columns is smaller than the previous result in DGPY20. And this compact metric greatly improved the sampling efficiency. So as for the comparison with the Genius Essential Simpler, our simpler achieved the same Gaussian quality with and their simpler you heavily use the float, but our simpler only use integers, so we can have better compatibility to constraint devices. And also we have the storage advantage, and both Genius Essential Simpler and ours runs in linear time. We also implemented our simpler and compared with the Genius Essential Simpler implemented in Palisade library. In this picture, we can see that our algorithm is as fast as implemented in Palisade. So next, we will show our new gauge subgaussian simpler. Our gauge subgaussian simpler is very different from the previous simpler. Our idea is to convert the sampling for arbitrary modulus to the easy and faster simpler for B power of B. Q is equal to power of B. This is a simple fact that for short x, if the inner product of the x and g is equal to u modulo b to the key, then the result of the inner product is in the site of u and u minus b to the key. So as for our simpler's output x, the inner x satisfies the inner product of x, and the gauge vector g is equal to u modulo q. We also limit the inner product result is in the site of u and u minus q. Notably, the value u and u minus q basically determines the last coefficient of the vector x. So our algorithm can be done by these three steps. First, we can choose the u prime according to some portability, and then we can sample the x prime is the first k-1 coefficient with the simpler of the q is equal to b to k-1 given u prime, and finally we could determine the x k-1 as per u and x prime. So as for the comparison with the Genius Essential and Prokop simpler, the GMP algorithms use the k-squared log b random bits, which was claimed to be most optimal in this paper. In fact, our algorithms result k log b random bits. Notably, our algorithm for arbitrary modulus needs an asymptotically same amount of random bits with on the power of b modulus. So we therefore believe that this is essential, the optimal in randomness cost. Our simpler is also simple and doesn't need a completed metric. So our simpler is easy to implementation. As for the quality, our algorithms achieved close or even better quality for practical payment. More important, our simpler is practical fast. We can see in this picture that we implemented our algorithms with and compared with the genius essential block algorithm implemented in Palisade library. You can see that our algorithms is about 1.3 to 3.2 times faster than the genius essential block algorithms. So that's all. Thank you.
Thanks for your nice talk. And are there any questions or comments? Okay, so let's close this session. Thanks for both speakers of this session.